So this textbook uses something called the best two analogy to describe what happens in your laser diode. Let's consider your semiconductor is a best tube, and probably you are tired at home and be comfortable to soak in hot water, this kind of best tube. And you have a faucet, just like the power source of it, the density, and it injected carriers. The carriers is the water. Alright, so there's some bad holes at the bottom. That means your best tube is broken. Some carrier injected will be consumed at the bottom, and it will be dominating when the carrier density is low. Those are non-radiative condition and the spontaneous emissions. As you inject more water inside, the water level or the carrier density start to increase because the recombination rate doesn't catch up the injection from outside. So the overall carrier concentration increases. But under some certain level, because it has a cavity and it laces, if it doesn't lace, you will keep increasing. Okay, so the depth of the best tube is the threshold carrier density. All carriers accessing the threshold NTH will be leaving the material as the stimulated emission or the lacing. So, if today's question is how to make this best tube better, we might start with some few ways. So let's define further what is better. The better part means I don't want to increase so many water to reach a steady state. I don't want to inject so many current, but I want to reach the stimulated emission, reach lacing. So what should we do? First of all, we should try to have a sight. What is that? Should I say? So we can try to stop the leaking from the bottom. First, we should try to reduce the non-radiative recombination. This is the most the useful and irrelevant to design. This is usually processing issue. That means you need to make your quality as good as possible. Secondly, we can also try to stop the spontaneous emission, because only a beta SP will contributing the lacing mode. The other mode will have no effect. Now that will be light, but that will be not the wavelengths contributing the lacing. So we might also consider to reduce the spontaneous emission. How do we do that? Since the constant B is a constant, we cannot do nothing about that. But we know that the spontaneous emission happens when it couples to a specific mode of such cavity. So we can try to reduce the available mode. So that will be about the concept of microcavity, to do a very small cavity close to its wavelengths to reduce the available modes, or by doing something else to reduce its density of state. It's also available. And also there will be some leakage from the faucet that doesn't even goes into your best tube. This is the term of the injection efficiency. So in this case, we want to try to make the faucet not leaky. So that means you need to eliminate all the possible leakage paths Like you probably want to optimize your band structure, so your carrier will be stopped by an additional structure. Because while you're injecting a lot of carriers by forwarding voltage, the band diagram will start to twist and become balanced. Then if you don't have a structure to stop the electron will overflow. Since the electron always have a higher mobility and a broader distribution in energy. So in this case, you need to do some design to stop the electrons rather than hold. Then we have something called the electron blocking layer. Quantum well fitness optimization. Why? Because if a quantum well is too thin, the hard carrier effect will take place. The carrier might not be captured by your quantum well, just go through it. So the quantum well, you don't want the quantum well to be too thin. But you also don't want the quantum well to be too thick. Because if in the extreme case, it will be a CCH laser. Or from another perspective, if the quantum well is thick, that means it will make you more difficult to fill this tank. Okay, so this is also an optimization issue. Then we can try to do all the rest of them. Then you eventually get a lower NTH for your laser diode. Or from the perspective of this equation, gain is equal to loss. We can say that we should try to reduce the loss. The optical loss here, for example, you want to optimize the doping profile. If the doping in concentration is too high, there will be a very significant free carrier loss. But if the doping level is too low, it will be pretty resistive. Then a resistive semiconductor gives you additional heat. Then additional heat will broaden the energy distribution of the carrier. So you need to have simultaneously manage different perspectives and know what happens after you taking specific direction from the perspective of electrical confinement and thermal management, something like that. So it's a very interesting topic. And another way is to that if the alpha and the alpha n is fixed, and I want the GTH to be low, then we can increase the gamma. If your optical cavity has a stronger confinement factor, that means your overlap of your active region with the optical fold, with the optical field is very strong. Then with the same level of internal loss and mirror loss, the threshold material gain will also be decreased. Okay, so there's so many aspects to consider to make a useful semiconductor laser diode and trying to make a better and better continuously. So here is an example of the threshold gain calculation. Let's consider a two-segment communication laser whose wavelength is 1.55 micron. Anyway, let's return to the question. So let's consider a 1.55 micron communication laser with two facets to form a fabric prototype laser. And the total length is 850 micron, which has a 600 micron passive region. Okay, so mostly passive. And the 200 micron, so it's passive and passive. So it's definitely a typo. 680 regions. I will correct that later. And the 250 passive region. Okay. Then the internal loss and the Mach effective index is here. The active region has also a higher loss. because surely this is just a number I give, but why I explain why this usually happens this way. The AT region is the part with current injection, so the carrier density of the cladding layer is usually higher. So it has a higher free carrier loss. So the loss will inevitably be higher than the passive part. Okay, and then the passive region is slightly lower internal loss. And then the NEFF is higher, 3.55 for AT region and 3.52. Since we don't want to deal with the transmission matrix yet, let's assume the optical mode will passing through this interference without reflection, or that will be another question. So that's not one we want to deal with now. Okay, so try to evaluate the threshold gain, the threshold modal gain, and the mode spacing. So let's start with the reflectivity of two mirrors. Since the reflectivity of first segment is 3.55, and this is the Fresnel equation for the reflectivity. So R1 is 3.55 minus 1 divided by 3.55 plus 1. The R1 is 0.56, 0.56, and the R2 is 0.558. Anyway, so we have the internal loss like this: LA divided by L times its loss. So it will be 800 divided by 850 times 20. And 250 divided by 850 times 15. So the internal loss, average the loss is 18.5. Okay, so then we can insert it into the mirror loss. Mirror loss is equal to 1 divided by L times ln 1 divided R1 and R2. Okay, so just put in numbers. And since this is micron, remember to transfer it into centimeter inverse, because that's the usually unit we use in the optical loss. That will make the number more common. Okay, so the answer is 13.7 centimeter inverse. Then total gain is loss times internal loss times mirror loss. Okay, so this is the threshold modal gain of such a laser. And the delta lambda, the mode spacing, just apply this equation. Lambda is 1.55 micron. And the NGA we use a 3.8 due to the previous slide, since it's a communication laser. Alright, so it turns out 3.72 times E minus 4 micron. So surely we should transfer a more normal number. So it's around 3.7 angstrom or 0.37 nanometer. Alright, so how do we describe gain? So we take a pretty long time to get the expression as G of n is equal to G max F2 minus F1. This is what we did in the earlier part of this course, and the F2 is equal to exponential E2 minus EFC. I hope you still remember that. Over KT plus 1 and over 1. And the position of Fermi level need to be estimated by the carrier concentration. Similar for F1 and FV. Okay, a carrier concentration decides your Fermi level. Decide your Fermi level, decides your F2 and F1. Then you know it's optical gain. So gain, the optical gain is a function of carrier concentration. But such a calculation is pretty lengthy. Yeah, and probably a little bit complicated. But anyway, but this is conceptually correct. But while we are trying to deal with a coupled equation like this, it will be pretty difficult to get a number here from this. So, in the perspective of device, we usually use a simple model with logarithmic model. It might either have 3 parameter or 2 parameter. So, if you try to do that with your homework, I ask you to plot the gain from low concentration to high concentration. Okay, so this is Professor's answer, the blue dots. Okay, then we try the two simple model. What is 2 parameter model? It's simply G0 times natural log n divided by NTR. If n is equal to NTR, G will be 0. Okay, so it's physically correct at the pressure transparent condition. And I tried to fit the exact solution by that procedure with 2 parameters. So the 2 parameter one is the orange one. The answer I used, the G is equal to 3026, and NTR is 2.48E18. It doesn't look too bad, except for the region with very low carrier concentration. Let's see what's the problem here. This model, although it is good, the prediction is not too bad, but it has a physical problem. If you don't learn the gain at the beginning, directly use this number, you might think when n is equal, it's very low, your gain will go to infinitely, minus infinite. This is not physical. Second, the n is also not bounded in the positive side. If you use this model, you might imagine if the gain is very high, the carrier density is very high, the gain will be as high as possible. This is also not correct. The gain will be bounded between minus Gmax and the positive Gmax. So this is just empirical. It is useful while we are trying to discuss the ray equation with carrier concentration in between, usually between the 1E8 to 1E9 or 2E9 in such a region. It describes the curves actually pretty good. That will be more useful than incorporating the whole procedure into the ray equation. That will be things pretty difficult to solve. And there's also another 3 parameter model. We just added the NS here. This revision fixes the case that when n is equal to 0, it doesn't go to minus infinite. So the applicable region will be a little bit better. It goes to the low carrier density side, but it is still not good enough, because when n is really large, it will give you an illusion that it will go to infinity, which is also not correct. But anyway, for the people doing the semiconductor laser for use, this is also already pretty good enough. Since if the laser need to be pumped very high, it's not good use at all. Yeah, we always use laser with acceptable carrier density, threshold current density, and the carrier density. So this model might be good enough for you to evaluate its properties like speed. Alright. So the two-parameter model will be cleaner since we can do it with analytic expression. And we can define a term called differential gain with the two-parameter model. The differential gain is usually written in the lower letter A. It's dg over dn under specific carrier density. So if you take that, it will be G0, the first parameter, divided by the carrier density. This will be used in the next week.